Okay, now come towards electrophilic addition once again. Electrophilic addition. First of all, what is an electrophile? Electrophile. Electrophile mean electron lovers. Electron lovers, the species, those are having positive charge, they are said to be electrophile. That is a general notation of electrophile. So any species, any atom, any molecule, if it is having positive charge, I mean all positive ions are said to be electron lovers, they are said to be electrophile. And in addition to that, any species that is having basically electron deficient center molecule or electron deficient atom in its center, for example AlCl3, in this case this aluminium is not having complete octet. This aluminium is not having complete octet. There are basically 6 electrons, so it is electron deficient molecule. Electron deficient molecule are also said to be electron lovers, electron seeking molecule. So yes, it can also be act as electrophile. So generally any species that is having positive charge, I mean highly electron deficient molecules, and any molecule that is not having any positive charge, but if the octet is incomplete, if any molecule that is having any atom with incomplete octet, then that molecule can also act as electrophile. In contrast to this electrophile, there is another molecule or other term is nucleophile. Nucleophile. What is a nucleophile? That is nucleus lover. Nucleus lover are having generally, that is the notation of nucleophile. Nu stand for nucleophile. So any species that is having one lone pair, at least one lone pair, and that can donate the lone pair of electron, it is said to be a nucleophile. And same thing, any species that is having negative charge on it, it's said to be nucleophile, like Cl negative ion. In this example, like NH3 that is having one lone pair. In this category, Cl negative ion, OH negative ion, and Cn negative ion, for example. Any species that is having lone pair and it can donate the lone pair, it is said to be nucleophile. One example is ammonia, and the second, the most common example is water molecule. So they both molecule are simple molecule. They are not any positive or negative ions, but they are having the lone pairs on it, on their main electronegative atom, and they can donate the lone pair of electrons. So they are said to be nucleophile. These are all said to be, these three are negative charges: Cl negative ion, OH negative ion, Cn negative ion, and they all are known as, are said to be, or act as nucleophile. So any species that is having lone pair, it is going to act as a nucleophile. Any species that is having negative charge, any negative ion, anion, can act as a nucleophile. And moreover, plus, in addition to that, all carbon-carbon double bonds are going to act as a nucleophile. This carbon-carbon double bond is having one pi bond, and other one is having a sigma bond. So the pi bond of the double bond is basically going to act as a nucleophile. So these are the basic main categories of electrophile: 2 categories; nucleophile, 3 categories. And you should be able to design the different sort of mechanism if you are going to have the proper theme of electrophile. So you should be able to recognize the nucleophile, electrophile, and then you will design the different sort of mechanism. Then you would be able to draw or to report the mechanism. Now the next thing is I'm going to explain electrophile, electrophilic addition, and what is electrophile. As I told you, now I'm going to show you the specific electrophile. And one more thing, there's any partial positive charge species like H positive ion is also said to be an electrophile. So this is an electrophile. This molecule can act as an electrophile, and any full-fledged positive charge that also can act as an electrophile. So basically these are three type of molecules or three type of species can act as electrophile, and these three type of species can act as nucleophile. Now the next thing is how to write the electrophilic addition. So basically it is the property of carbon carbon double bond. It is property of the carbon carbon double bond that whenever it is going to react with any other species for addition reaction, then it is going to react with electrophile. As I told you, this carbon carbon double bond is going to behave as a nucleophile, so definitely it will attract electrophile. These two species are having opposite nature, opposite charges, you can say. So this carbon carbon double bond is behaving as a nucleophile. All carbon carbon double bonds are said to be or supposed to be nucleophile. So it is a nucleophile when any, for example, when any halogen, I am going to react it with Cl2. This is the molecule of Cl2. Initially, chlorine molecule is non-polar. There is no partial positive or no partial negative charge on this molecule. But when the chlorine molecule go into the proximity of carbon-carbon double bond, so due to the, neighboring carbon-carbon double bond, halogens, those are initially non-polars, but they are going to have polarize. This carbon-carbon double bond is going to polarize this molecule. Due to the proximity of carbon-carbon double bond, halogens get polarized. So I am going to write partial positive charge on this Cl and partial negative charge on this Cl. Why they are getting partial positive and partial negative charge in spite of having the same electronegativity of these both Cl? The reason is its proximity effect. This carbon-carbon double bond is basically going to create polarization in Cl-Cl bond. So number one, as I told you, it is a nucleophile and it reacts with an electrophile. Number two, whenever any halogen, for example, non-polar molecules, let's suppose halogen, when it is allowed to react with this one molecule, then the first step is there is the polarization of halogen. Now, what is the second step? I'm going to mark the curly arrow at this time. This pi bond, carbon-carbon double bond, attack on the partial positive chlorine Cl atom. At the same time, this Cl-Cl bond is broken. So this is the second arrow. I will mark first arrow when the carbon-carbon double bond is going to attack on this Cl, that is partially positive Cl. Full arrows. Because this is attack of full bond, full pi bond, and there is a shifting of full pi bond. This bond is going to be broken unevenly, that is said to be heterolytically. So these are marked as a complete arrow, as a full arrow. Now what is the next? Next is the intermediate. What is the intermediate? As you have seen that we have ethene and one bond left, CC bond left over here, and two hydrogen with each carbon will remain intact. Now this is the simplest way. Then this bond will be shifted toward this Cl, and this is the CCl, new bond is going to be formed. New bond, that is called CCl bond, is going to be formed. And what will happen on this carbon atom as you have removed its electron, as its gain full positive. It has now become a positive charge. Yes, good. Now it has become carbocation. And this overall, and plus, yes, we are having Cl negative charge with 3 its lone pairs. And this species, this carbon species is said to be carbocation, and it is said to be overall generally carbocation intermediate. Carbocation intermediate is this one. So first of all, there are, Cl, partial positive, partial negative, yes.
So what does intermediate mean?
Intermediate mean any species that is being formed before the formation of final compound.
Oh, okay, thank you.
Okay. Now, once again, I'm going to repeat my steps. Carbon-carbon double bond, when it is allowed to react with halogens, halogens get partial positive and partial negative charges. And that is because of the proximity effect of this carbon-carbon double bond. Now, when there is one partial positive Cl and one partial negative Cl, then this carbon-carbon double bond attack on the partial positive Cl, and this Cl-Cl bond is broken at the same time. This is a simultaneous process. And there is the formation of new bond, CCl bond, but this carbon has lose one electron, so it's going to have one positive charge over here. Now the next one is basically, generally the last step, I'm going to mark only one curly arrow, that is starting from this lone pair, and it is going to attack on this carbon atom. There are basically three lone pairs. On Cl, there is a one negative charge, so it is highly likely to be the attack of lone pair rather than the negative charge. There is the ratio is 3:1, three lone pairs, one negative charge. So there are more chances of attack of lone pairs. So that's more good. That is more appropriate. Finally, compound is over here. What is the final product? We are going to have this one product, and here second Cl, H, and boom. This is the final that is said to be 1,2 dichloro 1,2-dichloroethane, 2 carbon ethane, and so on. So this is the brief general shortcut mechanism of carbon-carbon double bond. So this is said to be addition reaction. As you have seen that only one compound is going to be formed, two basic small molecules are going to be added up, and there is formation of only one molecule. So that's why it is said to be addition reaction. The next thing is why it is said to be, its mechanism is said to be electrophilic addition. In first step, this Cl, that is partial positive Cl, and as I told you, any partial positive atom, any atom that is having partial positive charge, it is regarded as electrophile. It is regarded as an electrophile. So the first step, we are going to add electrophile. So the basic name of mechanism is kept on its first step. So in first step, the positive charge is being the part of the carbon-carbon double bond, or this carbon molecule, this carbon organic compound. So that's why in first step there is introduction of a partial positive species that is basically electrophile. So that's why it is said to be electrophilic addition. Now come towards another example. Now this time I'm going to add basically HCl, but I'm changing the alkene as well. For example, I'm having propene CH3CH double bond CH2, and I'm going to react it with HCl. I'm going to write HCl like that. Now this time HCl is a permanent polar molecule. There is no need for the charge separation. It is already having charge separation. Partial positive Hs over here and partial negative Cls over here. That is the permanent polar molecule, and this is the permanent dipole. So whenever this molecule is allowed to react with any alkene, then similarly there is attack from carbon-carbon double bond. Carbon-carbon double bond, negatively charged species or nucleophile attacks always. So this carbon-carbon double bond will attack on this hydrogen first of all. And at the same time, as I told you, this HCl bond is broken. This HCl bond is going to shift on the Cl atom. Now, what is going to be formed? What is the next step? In next step, we will write carbocation intermediate. Two type of carbocation intermediate may be formed. Number one, I am going to write it over here. CH3, CH, single bond. One bond is broken, single bond, CH2 and H. And this carbon is having,
Stage 3.
yes, good. And this carbon is having positive,
Positive, not partial.
full positive charge, yes.
Full
So
positive
this is
charge.
the one possible option for the formation of intermediate. Now there is a next chance, next possibility of the intermediate is this one. If I'm going to write CH3 over here, and this H
Hydrogen
is
on the middle.
going to the middle carbon, yes, good. So it will be CHH, and now this time this one carbon, the ending carbon, this carbon is going to
Positive
have
charge.
positive charge. And as you have seen, one bond has been shifted, so one bond left, it is positive charge. What is the difference between these two carbocations?
So in the position of the H,
Basically, it is
CH3.
said to be primary carbocation.
Okay. And you
Primary
said first was
carbo,
secondary.
what?
The example above is secondary carbocation.
Good. It's a secondary carbocation. Secondary carbocation. And you must know, you must remember that secondary carbocation is more stable than primary overall. Tertiary carbocation, tertiary carbocation is more stable. It's having more lifespan
Secondary.
than secondary. And secondary carbocation is more stable than primary carbocation.
So what does this stability mean?
Carbocation, एक minute. Basically, tertiary carbocation, if there is a formation of two different carbocation, one is tertiary and other one is secondary, if there is any possibility of transformation, then secondary carbocation will change itself into tertiary carbocation. Generally speaking, if a carbon is having positive charge on it, then this molecule is going to be or supposed to be less stable molecule. I mean, it is not the property of the non-metal to bear to have positive charge. It is the property of metal. But if the carbon is has to gain or have to gain, the positive charge, then they are generally are supposed to be less stable. So, if there are, for example, just have a look. This is basically secondary carbocation, and it is said to be primary carbocation. In this primary carbocation, only one immediate group is over here. That is basically indirectly it is donating the electron to decrease the thrust of this positive charge. Carbon has lost one electron, and here immediately there is only one carbon. CH2 group, CH3 group are said to be or supposed to be electron donating group. They are donating electron to decrease, its loss, to compensate its electron loss. So they are donating electron up to some extent. But in this case, this is secondary carbocation. Our electron donation is coming from both sides, from two sides. In this case, electron donation is coming from only one side. So this carbon is having more satisfactory level. Although they both are having positive charge. They both are having positive charge, but this is said to be more stable. It can survive for long time interval because it can, its neighboring group CI3 or CH2 group are indirectly compensating or trying to compensate its loss of electron. Here there is only one group that is compensating the electron, right? And in case of tertiary, this is a tertiary carbocation. Whenever, let's suppose it's going to be formed, this is called tertiary carbocation. And you can see that here are three groups. Those are basically donating the electron to this central carbon. So three group are going to compensate the loss of electron of this carbon. So that's why this will be more stable. Once I told you, the carbon or any non-metal, if it is going to have a positive charge, it becomes unstable. It's not the property of non-metal to have the positive charge. Basically, this is the property of the metal to become a positive ion or to gain or to get positive charge. But once there is a positive charge, then its neighboring group are trying to encounter its positive charge impact. Larger the group surrounding the carbon, that is going to compensate the effect of positive charge up to the maximum level. And in this case, this is the bottom level, you can say. There is only one group that is going to compensate, so it cannot compensate efficiently. There are two groups to compensate the effect of positive charge, and here are three groups, those are compensating the effect of central positive charge. So that's why the lifespan of this carbocation, tertiary carbocation, is higher as compared to secondary carbocation, and secondary carbocation is having more lifespan than primary carbocation. So what happened basically? Most of the molecule will change itself. There is a transformation of molecule. It's called rearrangement of the molecule. Why and how basically they are going to rearrange? Why they are rearranging? Because the next form is more stable. And how they are basically rearranging? Here is a shifting of positive charge, and this H will be shifting over here. So this is called rearrangement, and we can call, just like transformation. So it's the rearrangement or transformation, and primary carbocation after some time changes itself into secondary carbocation. So almost 99% population in your reaction mixture, in your glass, in your vessel, in your test tube will be the secondary carbocation. So the next thing is major product will be formed. Major product will be formed with respect to secondary carbocation, because there are more population of secondary carbocation, so definitely it will go into the next step. What is the next step? Here we have made Cl negative charge. This portion of the molecule is going to change into Cl negative ion. So lone pair, lone pair, lone pair, and this time this Cl may attack on this carbon atom to make 2-chloropropane. That is a major product. It is called major product. CH3, CH, and CH3, and here is Cl. It's a 2-chloropropane. It is called major product.
Yes, sir.
And yes,
So secondary carbocation is the one that is 99,
that is,
the one that is 99% formed,
yes.
and tertiary carbon.
No, it's a primary. The second one is primary. I told you the comparative percentage with respect to secondary and this one primary.
कौन सा ज़्यादा होता है सर?
Secondary,
ही होता है.
secondary.
अच्छा.
This primary is changing itself into secondary. So definitely final shape of this intermediate, most of the population will remain in this shape, in this form. Got it? Okay. So this compound is formed, and this is also said to be Markovnikov product, or this addition is called Markovnikov's. There is no need.
Addition of chlorine to alkene.
No, in shortcut way, I'm going to tell you this hydrogen, this positive part is going to be added to that carbon that is having already more hydrogen. This partial positive hydrogen, when the bond is broken, when double bond is broken, it will go to that carbon that is having already more hydrogen. So it will snatch this hydrogen, and the product form is said to be major product. So Markovnikov's tells us what is the shortcut to check the major product molecule or the formula of the major molecule. So whenever you are going to react, unsymmetrical alkene with unsymmetrical reagent. So definitely when the bond is broken, then there are two options. This H may go with this carbon, or it may go to this carbon. So if you want to check the the product, main product is going to be formed, that is having this CH3 group. H will be gone, H will be donated towards that carbon, that doubly bonded carbon that is having already more hydrogen. So it will be major product, and it will be in 99%, you can say. Now, what is the minor product? I'm going to write it with the pink pen. This compound, this intermediate, the remaining part of, I mean, almost they are 1% usually, they will be changed into minor product. So, what is the answer? I mean, what is the mechanism? Generally, how to write the answer? I mean, I'm going to attack this Cl on this carbon atom, and finally we are going to have 1 chloropropane, 1 chloropropane. So these two are called isomer. One is minor, other one is the major. Both products are formed. One is major, other one is minor. So in this product, you can once again see the hydrogen has gone to that carbon that is already having more hydrogen. So doubly bonded carbons are going to react in this case, in this whole mechanism. So I told you to write the, I mean, how to choose the mechanism, how to write the mechanism, and if they're asking to write the mechanism of the minor compound, minor yield, minor product, then you will go through this route. You will write, I mean, the first one is a similar one. Next, where is the change? There is the change. Change is lying over here whenever you are going to make the primary carbocation. Then you will have to decide either you want to make the primary carbocation or you should make secondary carbocation. So, once again, if they are asking to write, to design, to make major compound, then you will see which one is the major. This hydrogen will go to this carbon that is having already more hydrogens. If they are asking to make write the minor compound or minor product, then this hydrogen will go to that carbon that is having already less hydrogen. So whenever this carbon-carbon double bond is broken, then these two carbons get one portion. I mean, one portion of the other molecule. As you have seen that this bond is also broken. So one portion goes to one carbon, other portion goes to the second carbon. I mean, two doubly bonded carbons. And here is the basic scheme and so on. Now, as I told you, tertiary carbocation is more stable than secondary carbocation, and that is more stable than primary carbocation. The basic reason is there are CH3 group, and all CH3 group, all methyl group are showing electron donating effect. They are electron donors, and it is said to be as inductive effect. This property is termed as inductive effect. So all CH3 group are showing positive inductive effect. They are donating the electron. Donation of electron is positive inductive effect, and snatching the electron, like any electronegative atom, it is supposed to snatch the electron. It is said to be negative inductive effect. So because of the positive inductive effect, if there are more CH3 surrounding the carbon atom, they are going to decrease the, compensate the deficiency of electron on that carbon, and so on. This is the basic general mechanism step of electrophilic addition. Whenever they are asking to write the electrophilic addition, you will repeat all these steps. Got it?